A huge goal for astrophysics is to work out whether Earth is special or not. Are there other Earth-like rocky planets out there with thick atmospheres and life-giving oceans just the right distance from their stars so they're not too hot and not too cold for life to flourish? Or did we just win the cosmic lottery? Now, there are a few Earth-like planets that we've managed to find so far that we know are at least roughly Earth-sized and the right kind of distance from their star. But what about their atmospheres? Are they also Earth-like and can maybe support life? Well, that question is a little bit more difficult to answer, but all our hopes currently are on the James Webb Space Telescope. And in particular, a lot of excitement has swirled around the TRAPPIST-1 system, a star 40 light years away from Earth with 7 known planets orbiting it, all of which are roughly similar in size to Earth, and 4 of those planets are in the habitable zone, where the amount of light that they get from their star would mean the planets have a temperature that's not too hot and not too cold for life, at least as we know it here on Earth, to exist. We've already heard that the 2 inner planets, TRAPPIST-1b and c, have no atmospheres at all as far as JWST can tell. And it's been a very long wait to see the results of the JWST data for those 4 habitable zone planets, as the data has proved very difficult to both collect and then make sense of. But finally, this past month, Piaulet-Ghorayeb and collaborators published this paper with their results on the atmosphere of TRAPPIST-1d, the planet in the system that's right on the edge of the habitable zone around its star. And unfortunately, it's not the news that we were all hoping for. It doesn't look like TRAPPIST-1d has an atmosphere like Earth's, and while Piaulet-Ghorayeb and collaborators ruled out a few possibilities of what it could be like, we still don't know for sure what kind of atmosphere it has. So, in this video, we're going to dive into all of this and chat first about why there's so much hype around the TRAPPIST-1 system, then chat about what Piaulet-Ghorayeb and collaborators have found with JWST for TRAPPIST-1d, and finally, what this result means for the rest of the planets in the TRAPPIST-1 system. So let's start with the first on that list there, why there's so much hype around TRAPPIST-1. So for context, these 7 planets in the TRAPPIST-1 system were only confirmed back in 2017 after a dedicated observing campaign by Gillen and collaborators over 2 years. And there was a huge amount of excitement around this system because, this was a 7-planet system. That's not a far cry from the 8-planet system of the solar system. This wasn't just, like another star that had been discovered with like 1 or 2 planets orbiting. Here was a proper planetary system. Not only that, but all those 7 planets were roughly Earth-sized, meaning they were very likely to be rocky planets like the inner planets of the solar system. And despite the fact that the star was a red dwarf, so very different from the sun, it's a lot smaller and cooler, because the planets were orbiting so much closer in, orbiting closer to their star than Mercury does to the sun, that still put 4 of those planets in the habitable zone, where it's not too hot or cold for life as we know it to exist. You've got the planet TRAPPIST-1d on the inner edge of the habitable zone, along with E and F in the middle, and then G on the outer edge. Now, just so there's no confusion about names and terminology, all planets are first and foremost named after the star that they orbit around. So the star here is called TRAPPIST-1, and since that's like the only star in this system, it's not like a binary system of 2 stars, that makes it TRAPPIST-1a with a capital A. And so then you start naming the planets from the letter B, B, C, D, E, F, G, etc., either as you get further away from the star or in the order that they're discovered. But usually because we discover the planets further in systems first, just because they're easier to spot, usually you end up going in that order anyway. And of course, with this discovery came many questions about their potential habitability and of course their atmospheres as well. Especially whether a red dwarf star like TRAPPIST-1 can even host habitable planets. Now, the inner planets in this system, 1b and 1c, were actually discovered first, and then the other 5 were then discovered afterwards. So 1b and 1c were actually observed by the Hubble Space Telescope in 2016, and the results were published by DeWitt and collaborators. Now, what they did to study the atmospheres of these planets was wait for the planet to pass in front of its star and block some of the starlight in what's known as a transit. It's how we actually detect a lot of planets are there in the first place. But if you take the light before the transit of just the star, and then during the transit, and actually take one from the other, you'll be left with just the light that's passed through the planet's atmosphere, so that you can see what effect, if any, the planet's atmosphere had on the light. So if the atmosphere had molecules like water or carbon dioxide in it, they steal away certain colours of light and leave behind a fingerprint to let us know that those molecules exist in the atmosphere of that planet. And so this is what DeWitt and collaborators did for the 2 inner planets, B and C, and they found that there wasn't much there in the way of atmosphere as far as they could tell with the Hubble Space Telescope data. Because this is the thing, the signal they got with the Hubble Space Telescope was very weak, so there was always the hope that the James Webb Space Telescope, JWST, would be able to reveal more here because it was more sensitive and has a bigger mirror so it can collect more light. But since then, both Green and collaborators and Zebra and collaborators have published work using JWST to show there's no evidence for TRAPPIST-1b having an atmosphere, kind of like Mercury in our own solar system, and then evidence for TRAPPIST-1c maybe having a very, very thin atmosphere. Now, we've always known that these 2 planets were the closest in to their star, and so there wasn't much hope with them in terms of habitability necessarily. They were the ones of this entire system were most likely to just be bare rock planets like Mercury, and JWST has shown us that's most likely the case. The hope and the hype instead has been on the planets that are in the habitable zones, the planets D, E, F, and G, which again, had their atmospheres first looked at with the Hubble Space Telescope by DeWitt and collaborators in 2018. Now, you're a lot more limited what you can do with the Hubble Space Telescope HST versus JWST. First of all, you're observing invisible light, not infrared light, so you can see different molecules' signatures. The telescope mirror that collects light is also smaller, so you're really limited on the data that you can get because the signal isn't very strong. Really, the only thing that you can sort of say for definite with the Hubble Space Telescope is either is there no atmosphere or is there a big, thick gas giant atmosphere like the likes of Jupiter? So DeWitt and collaborators found that for TRAPPIST-1d, E, and F, they could say for definite that they didn't have thick hydrogen gas giant atmospheres. But TRAPPIST-1g, they couldn't rule that out. Perhaps TRAPPIST-1g is something kind of like a mini Neptune out on the edge of this planet system, just like Neptune is out on the edge of our solar system. But for the other 3, it was very interesting that the Hubble data didn't suggest they have no atmosphere, but that they also didn't have thick hydrogen atmospheres either. So this is where a lot of this hype comes from, right? This data from the Hubble Space Telescope suggested that it was somewhere in between no atmosphere and a big thick hydrogen, gas giant atmosphere. Maybe for TRAPPIST-1d, E, and F, they had something like an Earth-like atmosphere, which, who knows, might be habitable to life as well. But answering that question is where you need JWST. You need it to look in infrared light. That way you're sensitive to these fingerprints that are left on the light from the molecules in the atmosphere, like water and carbon dioxide and oxygen. So that's why there's been so much hype specifically around these planets in the TRAPPIST-1 system and JWST observing them. Which brings me to this study by Piaulet-Ghorayeb and collaborators who used JWST to do exactly this and study TRAPPIST-1d's atmosphere. So TRAPPIST-1d is around about 80% of the size of Earth, but only 40% of its mass, so it's a little bit less dense than Earth. It's only 2% of the Earth-Sun distance from its star, but crucially, it still gets around about the same amount of light from its star as Earth does from the Sun. Which brings me to part 2. What Piaulet-Ghorayeb and collaborators found with JWST for TRAPPIST-1d. So here, you can see the raw data that the telescope first records, right? The brightness of the star TRAPPIST-1 before, during, and after the transit of the planet TRAPPIST-1d in front of it from our perspective. They then isolated the light that passed through the planet's atmosphere to get this trace of how much light at each wavelength the planet's atmosphere allowed through, and that's what you're now seeing here. Notice the vertical axis here is transit depth. So the more of a molecule there is in the atmosphere that likes to steal that specific molecule away. I know that this axis is flipped compared to like the little graphic that I just showed. Instead of amount absorbed, it's transit depth. So just bear that in mind. So the black circles here show the data points with the uncertainties on that data shown by little black lines coming out of each circle. And hopefully what you can see here is that the data shows that the signal is pretty flat, right? There's not much change from one wavelength to the other that's seen. If you compare that data though to what's seen by JWST for like big, thick gas giant planets like Jupiter, so here the white points are the data and they have those uncertainties as the little lines again, which you'll see are a lot smaller because the signal is much stronger because the atmosphere is so much thicker. And you can see very clear influences of water and carbon dioxide absorbing the light as it passes through the atmosphere. Whereas here, for the TRAPPIST-1d data, there's just none of that. Here's a closer look with, different colored lines showing like the expected signatures you get from different molecules that are overlaid. And when Piaulet-Ghorayeb and collaborators try and fit for these molecules, they don't find any evidence that the atmosphere contains any significant concentrations of methane, carbon monoxide, water, carbon dioxide, or sulfur dioxide. But there does seem to be a strong concentration of ammonia at first, but Piaulet-Ghorayeb and collaborators traced that back to actually contamination from the star itself fluctuating in brightness during the planet transit. And when Piaulet-Ghorayeb and collaborators looked at the density of the most likely model atmospheres, they found that the very thin atmosphere models best fit the data. Something kind of like modern day Mars. But also, they couldn't rule out thicker atmospheres with high clouds that block a lot of the atmospheric features, maybe similar to a modern day Venus. Neither of which, modern day Mars or modern day Venus, do we think are currently habitable, as far as we know. So this was not the news that we were hoping for TRAPPIST-1d, which brings me to finally, part 3, what this result means for the rest of the planets in the TRAPPIST-1 system. Well, first of all, it does cast a lot of doubt about whether planets in orbit around red dwarf stars are even habitable at all. Because red dwarf stars pose a lot of problems when it comes to habitability of planets because they give off a lot of deadly radiation. Because they're so much smaller, you get a lot more dramatic distribution of heat around the star's atmosphere. So as heat rises and falls in the atmosphere of the star itself, that sets charged hydrogen particles also rising and falling, and moving charged particles gives you a magnetic field. Those magnetic fields then get all tangled and eventually get released at the surface as extreme flares of X-ray light, way more energetic than anything we see for the sun. That radiation then bombards the planets, which can strip away any loosely held atmospheres, which of course could then be damaging to any current life or burgeoning life on those planets. But that is still speculation. We still need to prove that that is the case. And a few planets with no or very thin atmospheres very close in to red dwarfs isn't enough evidence to support that idea fully yet. So yeah, we are going to continue to study the atmospheres of planets orbiting red dwarf stars, not least because red dwarf stars are the most common star in our galaxy. And if it turns out that planets can hold on to their atmospheres in orbit around red dwarf stars and all of their harsh radiation, they should be able to do it anywhere. But what does this all mean specifically for TRAPPIST-1e, F and G, the other 3 planets in this system also in the habitable zone? Well, the further they are from the star, that means they're further away from that harsh radiation, so they should have a better chance of holding on to any atmosphere. The bigger problem though is that we're right at the limit of what we can actually achieve with JWST. Because they're further away, when they transit in front of their star, they don't block as much of their star's light. So less starlight passes through that atmosphere and then the signal you get out at the other side is a lot weaker. So unless their atmospheres are very thick, it's going to make this process very difficult. And from what I can tell and share from speaking to my colleagues is that this really is the first big hurdle that people are running into when it comes to analysing the data that they do already have, that JWST has observed transits from TRAPPIST-1e, F and G. They're finding that they need to observe more and more transit to sort of add all of those signals together to get a stronger one, which means waiting around for more transits but also waiting around for more JWST time, which is very competitive. I did already make a video a few months ago about a study that simulated the TRAPPIST system and found that if TRAPPIST-1e started out with a very thick atmosphere, it would have had some of that stripped away, as TRAPPIST-1 was particularly volatile after the star first formed, but as it settled down and gave off less radiation over time, the simulation found that TRAPPIST-1e could hold on to a habitable atmosphere. So not all hope might be lost yet, and I'll link that video down below if you want to check it out. But while I was editing this video, we also saw the release of 2 new papers, one by Espinosa and collaborators and one by Glidden and collaborators, that reported on the atmosphere of TRAPPIST-1e as seen by JWST. I'll be covering that in my Night Sky News video for this month in a couple of weeks, so look out for that because the data is really intriguing. It might support the idea of a nitrogen-rich atmosphere with some methane in there as well, but I'll make sure to read up on those papers and report back to you very soon. But all of this to say is that even though it's been a few years now since JWST launched, we are still just getting started when it comes to using JWST to study the atmospheres of Earth-like planets. We're just learning still, where that line might be between planets that can hold on to their atmospheres and those that can't, all to better understand where life might be able to thrive out there in the vastness of the universe. But Piaulet... Ooh, my shoulder just cracked. Did anybody hear that? Ugh. I think that was good. Right, I'm gonna go have some lunch.